Well, thank you for inviting me to give this talk. It's a pleasure to be here. Ben, I think yesterday said that Jeremy hired him, and it's not exactly true, but it's almost true in my case. When I came to Toronto with the interview, Jeremy was acting chair, but not exactly in the department where I was applying, in another campus. And I don't think he was doing well. Actually, he was very busy, but mostly working with Alejandro on different problems. And then we had 3 papers together. It was much later. And I think I hope it's not the last 3 papers, but it was a while. It was 10 years since we wrote one of them. So let me just say that maybe the title is not reflecting what I want to explain. It is a certain way of thinking about KPZ problem, which started with maybe our paper with Yuri Bakhtin and nonlinearity in 2018, but I think we now have better view of what we're proposing here. And maybe in more general form, it would be something like that, that if we look at the KPZ problem, the problem of polymer type, or say last passage percolation, then we have geodesics, and geometry of the geodesics, and their lengths, which is reflected through Airy processes and stuff like that. And what we are proposing is that basically we can disconnect these 2 things, geometry and the lengths of these geodesics. So what I will discuss how to construct universal object, which doesn't actually require KPZ setting very much, but maybe some more general setting. But I will not be discussing what are the lengths of these geodesics. So the matrix will not be there, but the shape and the statistics of their shape will be there. And I would say that's not a unique situation because we were used to the fact that random matrices, they have the lengths through the eigenvalues of these random matrices, but they don't have geometry. So they don't have geodesics, but there's a matrix. And we're used to it. So here it's counterpart. So we will have a geometrical object, but not the lengths. All right? And also advantage of what I'm saying, but it's mostly conjecture, but there are arguments why these conjectures hold. And this would give more general view of universality of geometrical object related to KPZ, and also would probably provide more broader context where you can observe it. So let me start from the following picture. Later I would consider more general setting. So I would consider say first passage percolation. So that will be my time, that will be my space, so it's a disordered media. And I would consider stationary situation. So I would consider infinitely long passes going down. So it's not on a finite stream, but infinitely long pass. So from every point, there is an infinitely long pass, which is last passage percolation pass, or first passage percolation, depending how you set it. So this is from every point. And some points will have maybe 2 of such passes. This is points of shocks. But basically, from every point, there is a pass, and it's well defined. And it's another statement. It's not trivial statement, but there is a technology to prove that such infinitely long geodesics or rays, as Chuck would say, exist. And then I would consider very large time n, and then I would consider another large time n. And the sequence of the so and 2n and so on. And I would consider map going from here to here. So every of these minimizers goes to one of these points here. And then I would start minimizers from this level, not continue from this, from every point here and going down. And then I would have it, so it would be one map taking those points here, and would be another map taking those points here, and so forth. And I would take a limit when n goes to infinity. And in the limit, we're supposed to get universal object, universal maps doing this thing. Now, this map would have particular structure. When m is large, what you see, it will not like continuous picture. You see here, what we will see is the following, that if I rescale coordinate, the rescaling will be x n to the 2/3, and time also is rescaled, time times n, like here. So it will be unit time now rather than n. and F1 and F2 will be written in this rescaled coordinate X, well, we'll see that many, many points here will end up with one point. And this point can be determined by different means. Basically, in KPZ setting, it would be area sheet plus independent white noise here, and not white noise, but Wiener process here, and then minimizing function which was written many times. But anyway, they would end up with one point, meaning that here they're very close. And then it would be another interval where end up at one point, and so on and so forth. So what you get that each of this map Fi, first of all, they will be stationary. They will have the same distribution because they have the same construction. They're going to infinity. They all will have be monotone. Translation variant. I will explain what it means. Stationary in time. And piecewise constant. So the graph of such map would look something like that. It is diagonal. This is the scale X, and that is where we started with the image. It was something going along the diagonal random function, random map like this. And so that's a graph of particular typical phi I, and we have realization of this phi 1, phi 2, and so on and so forth. Now, what is crucial, it is monotone. The fact that it's piecewise constant, it comes from monotonicity. If you iterate monotone maps, they would have the property that in the limit they will be piecewise constant. They would have tendency to get points together with exponential rate, and then some people have to be separated because length goes to length. But they would have this. So that is important, and that will be just where you will converge. And now the statement, what does it mean that we converge to some universal limit? It means that this limiting object, this maps F1, F2, Fn, they're random maps. So we have sequence of these random maps. And then I would define realization procedure. So realization procedure, realization transformation, acting on a sequence of stationary sequence of monotone maps. Now, I didn't explain what means translation variant. Translation variant means that Fix is equal to X plus stationary process. So they're stationary along the diagonal and weakly depending on faraway things. The thing does not have a lot of correlation when points are far apart. All this is random. So I have this random sequence of maps and produce another sequence of maps. So in dynamical systems, randomization, which we recently introduced statistical mechanics, where you kind of consider big and bigger block of spins, you consider more, you iterate kind of longer and longer time. So you iterate dynamical systems, maps, and then you rescale X. And that's exactly what we'll be doing. So in the easiest way, it will be the following transformation. I would consider G1 will be the image of this thing, sequence. It will be such a sequence, and say G1 will be just iteration of F2, F1, but we'll rescaled X and 1 X. And then G2 will be also 1 over beta F3, F4, F3, and so on. So I'll just determine what beta is in a moment. But we're basically going from time interval corresponding to n to time interval corresponding to 2n initially. So we enlarge our time by 2. And basically, we have to rescale X by 2 to the 2/3. And that will be exactly the scaling. But I define it not for this point, for any sequence of maps. So we have this stationary sequence, I produce another sequence. So what will be beta? Well, we can fix coordinates here, can scale here. We can fix it by assuming that average value of the image of point 0 square is equal to 1. So that will be fixing scale. And so then I would determine beta by just assuming that beta is such that average value of G1 0 square is also equal to 1. So that's uniquely determined beta as a forgiving stationary sequence, and you get another stationary sequence with exactly the same normalization condition. And so what you build up here in KPZ, it would mean that the sequence you build is the fixed point of this transformation. So in KPZ case, you get particular sequence.
Why you're scaling x by beta and you're scaling the thing by 1 over beta?
Because in dynamics, it's an image should be scaled in the inverse of that. So, right? So whenever you rescale x, beta, it's not time you're rescaling here. You're rescaling also x. So inverse, it's always like that. That's right rescaling in dynamics. And so this is a fixed point. This is particular sequence of maps which you get as a limit in KPZ. That will be the fixed point of this transformation. And so the conjecture in case of KPZ would mean the following, that conjecture would say the following. Let me first evaluate it for the scaling to third. That this transformation R has a stable fixed point so it means that Rn for some sequence f will converge to the fixed point f bar when n goes to infinity with exponential rate, provided, and that's very important, that then they have the same scaling behavior. What it means is that the thing which we started from, which should have the following property, that iterating f1, f2, fn, so if you iterate it n time and apply it to 0, we get something order n to the 2/3. So if we start with something with a thing, we'll converge to fixed point. And that is conjecture. It doesn't require any optimization procedure, any variational principle, just require monotonicity. So basically, the idea here, hope, idea, suggestion is that one-dimensional situation is so rigid, they're not going through each other, they're monotone, that requesting certain scaling behavior doesn't give you a lot of room. You are very rigid, just one statistic consistent with this thing. But then you can, of course, ask question, why 2/3? I have very general scheme. 2/3 is just one number in the scheme. So you can consider this type of problem, forgetting about KPZ altogether, for requesting that this is behaving as n to some alpha. So the scale is given by some exponent alpha, which is fixed. And then conjecture said that in this case also there is a fixed point. There exists unique, stable fixed point, which is another sequence of maps, which will be denoted by f alpha bar. This is sequence of maps, which knows about alpha, and which will be stable in a class of maps with giving alpha. So if alpha is fixed, then they converge to this fixed point under this implementation. So basically, I want to separate two questions: the geometry of geodesics and statistics of geodesic lines and their lengths. There is a separate question which I'm not touching, but probably it can be touched, in this problem. If the statistics or geometry of what geodesic is giving, how many metrics you can invent which will be consistent with it. Maybe for some of alpha you cannot even invent such thing. But for 2/3 we know that we can through the KPZ. But maybe it's unique as well for giving geometry of the thing. This I don't know. Now, I put it this way, iterating f1, f2, just from point of, just to make it a little bit more, I don't know, transparent. Of course, you should do it differently. Nobody said that you should go with time interval of length 1. So you rescale your time, it will be 1s you're starting, and then t where you end the up. And so what you will have really will be what's called stochastic flow. And that's getting close to what Valent and Duncan is constructing, which is directed landscape. So you will have stochastic flow, which is giving by starting time s and end time t, and takes points. It's a map from which takes a rescaled point x and map it to a rescaled point y. Starting in time s, and s would be greater than t because my time goes down, and for any s and t, because you can go it from not such from any, take a stationary regime. And that is called stochastic flow. And what stochastic flow that means is that if you iterate s t and then s t u, then you get map from s to u. So they're consistent in this dynamic. That means it's a flow. And this flow, which is stationary, because if you meaning that if you add anything to s and t, it will be the same statistics. And all of them are monotone. And then radiation transformation is just rescaling. So you're going from s, say, 0t to s 0lt, but rescaling x by some factor beta depending on L x 1 over beta. That would be your transformation with fixing certain scale. And again, you want to say that there is a unique process of this type, which is consistent with monotonicity, the giving scale of scaling behavior. Giving with the exponent that will be s0 n of 0 will be order n to the alpha. Now this thing will give you already the shape of geodesic because you're varying s and t continuously. And the counterpart of this conjecture would be that this thing has unique statistics for this, which is consistent with transformation, which is rescaling, and converts to this to fixed point after when rescaling goes to infinity. So that is a point of view which we are putting forward and which we want to advocate. Now, again, if I constructed all the geodetic line, then I can ask the question whether how to construct the matrix which can generate it. And I don't know the answer to this question. But perhaps we can separate because I think mechanism is different. Mechanism for this doesn't require any minimization, just require monotonicity. Perhaps it's true, not everybody believes in it. But my experience with rendition can say that it's plausible that that is true. And then the Airy process and the stuff like this is just built up upon that, which is beautiful and universal, but it is two separate things. And of course, alpha here is any parameter. I would like to say between 1 and 0, but I will be more careful. I would say between 1.5 and 1. Because of what I explained, I don't want to go to the area where it's sub-diffusive. It's a little bit more dangerous area. Perhaps it's true, but I'm just putting forward this conjecture for these alphas. And of course, there are two very special values. There is alpha equal to 2/3, which is KPZ. And I'll say a few words about it in confirmation of this conjecture. And there is special value 1/2. So about value 1/2, we know a lot. Because this value corresponds to the case when this sequence consists of independent maps. So if maps are independent, identically distributed, then the exponent will be diffusive. It will be 1/2. And then we know what is a fixed point. The fixed point would be what is called, and I'll say a few things about it, it will be what is called time one map for coalescing Brownian motions. Which is, yes.
Is that a theorem that they're independent?
So no, the theorem is that if they converge to with exponential rate, converge to time of web for Brownian for fractional Brownian. Say it again. Of course, you need some tailwinds. Yeah, but very mild. No, but yeah, but they're really very mild. Actually, it reminds me very strangely mild conditions. So it's enough just to have ergodicity of the process GIX in X. So the decay of correlation X, basically very low, very mild conditions. And we do require 3 moments, I think. But yeah, this is the theory which we proved with Li and Li, and it's published. And, yeah. So in a sense, it was known for some time that topologically, so you see, I have to say that stochastic flows are normally obtained as a solution of stochastic differential equations, and then they correspond to independent pieces. So they would, by construction, will be independent, iteration of independent maps. And then it was known for some time that they topologically converge to time map for coalescing fractional Brownian, which we introduce. But it was no rate of convergence. What we proved with Ling, that rate of convergence is power law in n, which means that it is exponential in realization transformation. I'll say a few words about it. All right, so let me just put some motivation, some explanation why we believe it's true. So one I already said. So there is a process which is called coalescing Brownian motion. And it was introduced by Aratia in the late 70s. And this is the following process. Many people know it. So it's a well-defined process. Start at time 0 from every point of real line with independent Brownian motion. And then when two Brownian motions come to one point, they collide, they glue together, and they continue with one Brownian motion. And you have to walk a little bit, and actually not a little bit, to prove that it exists, because the continuum of this thing, and there's a problem related to that. But what you can prove, and what was proved by Aratia, for any positive time, if you start with a point, what you see that there are discrete set of points, random discrete set of points, which is reached by all of these Brownian motions. So basically it means that Brownian motions starting from one interval end up at one point, and then another interval, there's another point, and so on. They collide by this time t. So out of continuum, you get countably many points, and they're discrete. They don't have accumulation point between them. And so you can do this time one map would be just map corresponding to tau equal to 1. What will happen when we have time 1? And then there is well-defined map, random map, which takes these points from time 0 to time 1, and it will have the shape as a previous one, some kind of going along the diagonal. And this is time 1 map. And because of scaling relation between Brownian motion, you immediately can see that if you rescale, you get copy of this map by rescaling x and t. It's such a trivial speed. Actually, there are a lot of known, it's non-trivial map, and it's determined by 2-point processes. 1-point process and 1-point process, wow. And 2-point processes are correlated, strongly correlated. Otherwise, if they were not correlated, it will not go along the diagonal like that. But you can actually describe the correlation functions of these point processes. And correlation function is determined by Pfaffian. So not the terminal structure, but Pfaffian structure of them. And Pfaffian will consist of some Gaussian kernels, depending. So basically, you can calculate what is the probability that certain number of intervals, say 3 intervals, are empty, that there is no point inside them. And then taking n points of these intervals, you create matrix 3 by 6 by 6. 6 by 6 matrix, which will be based on the endpoints of these intervals. The matrix elements will be Gaussian kernels, and then the Pfaffian of this matrix will be giving you correlation function for them being empty. And it's known that it's enough to describe empty sets, to describe all point processes. So we, as I said, we proved with Lee and Lee, who used to be PhD student of Eurobachtin, and then postdoc in Toronto, that if you start with independent maps, they converge to this map with power law in n, if you iterate n of them, or with the exponential law, if you iterate. So you see, if you iterate n times this map, it means 2 to the n time. And 2 to the n time means power law, but that detail. So 2/3 is more interesting. So what we did, we cannot prove the result. What we did some numerical confirmation. We considered the process, which is not maybe well-defined yet, but we believe it can be well-defined, and we're working on it.
So the coalescing Brownian motion is alpha 1/2?
It's alpha 1/2, yeah. It will be diffusive. So actually, it's an interesting problem how to construct any sequence of that such map for giving alpha. It's actually non-trivial. It's not easy.
Can you do it?
Well, yes, I'm going to do it now. Yeah? So, but yeah, it's not so easy. But the candidate is the following. That's what we did in numerics. We consider coalescing fractional Brownian motion. So fractional Brownian motion, I usually say that everybody hates fractional Brownian motions because it's an ugly object. It's not Markovian. It's a Gaussian process, but it's not Markovian. It's very similar to Brownian motion, but working with it, it's a disaster because it's not Markovian in particular. And simple things, every simple thing is not easy to prove. But they have what is called Hurst index or Hurst exponent h attached to them. H equal to 1/2 is just Brownian motion. H greater than 1/2, they will be positively correlated. So the past correlates the future in a positive way, and H less than 1/2 is negatively positively correlated, and it's negatively correlated. And that's why I'm a bit unhappy with this case. I want to consider positively correlated case. And what is known is that if you consider Brownian Wiener process with fractional Brownian motion with Hurst exponent h, then it behaves like t to the 2. So it behaves like t to the h, which means that expectation of square behave like t to the 2h. So it does fluctuate according to t to the h. And so that what we did, we started from every point of the real line, this fractional Brownian motion. Of course, it was on a computer, so it was a discrete set of points. And then you have to decide. The difference is that when the two things intersect, you have to decide which one you use to continue, because they both remember their past. So the best variant, we tried different variants. The result was similar, but the best one was when two things collide, you toss a coin and decide which one you choose to continue, and then continue with that one. And then we consider type 1 map for such thing, and compare it to the maps which you obtained from last passage percolation. And on a statistical level, we see that they're similar. So strong evidence using different statistical criteria that they have the same statistics. Now you cannot prove they have the same statistics. Yes.
For what h?
For h equal to 2/3. You have to fix the scaling because that's how they fluctuate. Now that will produce one map, F1, but not the whole sequence of maps. So if you want to produce a sequence of maps, you have to do a more elaborate game. You have to consider what is called Brownian web or fractional Brownian web. So you start from different points, your fractional Brownian motions, but then it's more elaborate rule how you do when they intersect. So basically, what you want to do, we didn't do numerics on this side, we plan to do it. You have to do the following, that every point carries the time it started. And so if two things intersect and one started here and another there, this one is winning. So the older wins against younger, but if the same age that they are, you toss the coin. So this type of game, then it will produce many maps of this type. They will have sequence of maps, and then they should converge to sequence of maps. They would know about correlation, time correlation of this thing. But this was not done yet, and we didn't do it.
If you did the opposite rule with younger and older, would that lead to some terrible?
Well, because I want. Well, it's. Let me comment on it at the end of my talk, okay? I wanted to end by saying that it's a bit too late to congratulate Jeremy with his birthday, because it was on 20th of December, but it's not late to welcome him to the club. So it's a good club. The older winning, so it's okay. So basically, that is more or less what I know about the thing, and we believe that we can construct coalescent fractional Brownian motion, more or less the way it's constructed by Aratia. As always, anything is more complicated because of non-Markovian property, but there is a nice integral representation of fractional Brownian motion. Actually, I would say that when people discuss fractional Brownian motion, they normally cite Mandelbrot and Van Ness paper. But in reality, it was introduced by Paul Levy in early 50s when he was visiting Berkeley, and he wrote representation, integral representation for the process. But the only thing is that he started it basically from zero, and because of that, it was not translation increments were not stationary, so it was not translation invariant. But what Ness and Mandelbrot did, they started at minus infinity, and then kind of in a limit when you run it for a long time, they get to the stationary increments. That's not very big deal, but the idea was introduced by Paul Levy. And through the integral representation, so you can represent it as an integral with respect of Wiener process. It's very simple stochastic integral with non-random integrand, and then you can work with it and you can prove several things. So I think I would stop here.
A similar version of a coalescing table with the precedent?
I don't know. I don't know. But basically, for coalescing, you need that they wiggle a bit, a lot, and so they intersect a lot. And then the only difficult thing is to show that many of them die. And when you have discrete set of points, that's not a problem to continue them. So that's the only thing. But since they wiggle, they're kind of locally like Wiener, that's anything which will be wiggling will have chance to construct it.
Maybe I missed, do you have a prediction for the exponent alpha as a function of h?
Oh yeah, it's the same. Alpha is h.
Alpha equal to
Yeah, h is how you deviate them. Alpha is h.
Okay, any other questions? Oh,
Just for fun, if you try to take alpha to be less than a half, would you say something more continuous as opposed to like a step?
Say it again.
If you tried to do this with alpha less than a half, just for fun, would you see something more like continuous as opposed to like these steps? Like would you not see coalescing?
I don't know. Alan is not here, right? Come on. Alan is here. Is Alan here? No. Very nice paper. Actually, let me take it. There was a very nice paper written by Alan and Scott Sheffield around 2009, I think, when they constructed a random walk which converted to fractional Brownian motion. And their construction works only for alpha between 1/2 and 1. So what they did is the following. They said, so basically behavior will be the following. You want to decide whether you go to the right. What is random walk? You decide you go to the right or to the left. It's probability 1/2, it's normal random walk, converts to Brownian motion. But you want to do something for fractional Brownian motion, so you don't know what to do. You sample your past. And you sample your past with some power law behavior which depends on h. And then what you did there, if you went to the right, go to the right. If you went to the left, and you continue doing it. Now you start minus infinity. So basically you have infinitely sampling already done. And then because you already did infinite sampling, so everything is split in the classes. And you can show that for h between 1/2 and 1, you will have infinitely many classes. Then you sample plus minus 1 for each of this class. And that will give you exactly what you're going to do forever with your random walk. And this thing converges to fractional Brownian motion. And when alpha is less than 1/2, it doesn't. It's tempting to do opposite, sample and do opposite. But I think it will not work because diffusion will win. Square root behavior that would win against them to the alpha. So there is a problem constructing. It's a beautiful problem. Limit of Brownian motion. That's why I need to be careful about alpha less than 1/2. I don't know. I want to say that numerical paper, and I should have said it, of course, it was done by together with Lee and now Yin who is now a PhD student at Berkeley, unfortunately with Alan Hamon, but with someone else, but he's doing more applied statistics, but he was an undergraduate student in Toronto when we did this work. Thank you.